And so let me get this ready for y'all. And then you'll see an Excel file that just has one simple data set in it, but I'm gonna show you, you're gonna be able to do the things I'm walking you through so you can see what's happening. And the best part about it is they're just gonna see a file that says, data for 3/7/2025, and they're gonna have any clue what it means. And I will leave it up to y'all. It is your discretion whether you want to tell them or not. And that's perfectly fine. I'm not gonna fault anybody because it's like, hey, wait a minute, I was here. So, okay, let me pull this up. Okay, you should see, nope, you don't see it yet. You should see it, except I cannot click on an arrow. You should see it now, visible to students for, the data says, data for 3/7, except it's named wrong. So I apologize, it says 20205, which should be 2025. I can't edit the file name that I've already uploaded, or I can edit it on my point view, but it doesn't really matter what the file name says. Actually, I am gonna fix it because this is driving me crazy if I don't. Replace. I'm not, all I'm doing is changing the name of the file, the data's the same, so you can keep the one you have.
I don't know.
Have you downloaded it already? Okay, there you go. Just gonna pull this up real quick. So I'm gonna keep the boards down. I'm gonna write in this little small space over here with a few notes just to kind of like drive the discussion. But primarily we're gonna be working in this Excel file. So go ahead and grab it, load it, and we'll talk about it. Because outliers are only part of the story. Outliers obviously cause significant shifts in your data. That's not unexpected. But the real challenge comes from when data points are not outliers, but they have an undue influence in your system. So I want to talk about those. So let me bring these online. Close this. Let's pull down the data, the file you're using, so that we're doing the exact same thing. Hopefully those will come up shortly. Oh, I guess we could switch this. There you go. Now it should come up. Okay. let's go back to some simple definitions. Outlier. What's the definition of an outlier? Simple definition.
It's not fit for that.
What's that? Yeah, that's actually just a really good way to put it. It's just a data point that stands out. And we're going to say it's unusual in X or Y if you're looking at it related to two component positions. If it's just in X, it's one that seems out of place with the rest of it. And most commonly you deal with Y outliers, but X outliers are a thing, and I'll show you the difference between those in a second. Next thing I want to talk about, so let's go through an example of X versus Y outlier. So, an X outlier, I want to make sure that I get this right before I say this. Yeah. Is a value, bless you, where Y is in the expected range, but X isn't. What do I mean by this? Like, you have your X range, you see like all your values of X are between, say, 50 and 100. All your Y's are in range, other than your outlier, let me qualify that, are in the range of, let's say, 200 to 400. But your outlier, because we're talking about where the Y is in the expected range, so your Y is, let's say, let's say it's 275, so it's right between these, for Y equals that. But your X is something like 200. You're like, hey, I'm seeing a Y value that makes sense, but it's not matching, the X isn't where I expect it to be. Because we don't think of them as separated, but they actually are very unique. The way Y outliers and X outliers behave is very different, and so we're going to go through that. And of course, and I'm going to just say Y outlier, Y outlier is just vice versa. So that would be that the Y is, the X is in the expected range, but the Y is not. Pretty straightforward, right? Well, let's show what happens with these. So this is your clean data set. And so if we plot this guy, we're going to insert X, Y scatter. It flipped it, so let me fix my data. I gotta remember to put X first and Y second. So actually I'm just gonna do that. I'm gonna switch my data out. If I can get this to work. There we go. And then I'm going to I've got to get a new mouse. This is terrible. This way I have, because when it pulls your XY plot, it assumes the first is X and the second is Y. So I just want to get my data in the order so I don't have to deal with that anymore. I have to switch right now. So this is your clean data. And are there any points here that seem weird looking at it? Not really, right? I mean, they're pretty much all following a straight line with noise. That's expected. Nothing here jumps out as a bad data point. Would you agree? Yeah, cool. So let's start talking about what if we have a bad data point. So let's do an X outlier. So I'm just going to basically create them down here. I'll do it over here actually. So this is my X outlier data. So I'm going to start with the clean data, and then I'm going to manipulate one of the values so you can see what it does. And so for my X outlier, you'll notice that I've done something here where I have like this 6. Notice they're not in order. I did that so that I had the ones that I wanted to manipulate at the bottom. Makes it easier for me to find. So on this one, let's say instead of it being, we expect the X to be in the range from 1 to like 11, and they all fall there. But let's say, what if this is, instead of, let's see, let me read this right. It's 20 for the X, and our Y is 76. So still in the range. So let's go ahead and put this information so we have it. X range equals, we expect it to be like between 0 to, let's say 12, looking at it here. And our Y range we expect to be, this is just for bookkeeping purposes, so we can see it. We expect it to be really from about 30 to 80. That looks right here, right? Sorry, we go to 20, but we changed this one. I changed the wrong one, sorry. Let me put this back what it was. This was 50, this was 6 and 55, sorry. I changed the wrong one. So now our X layer here, we're gonna go 20 for our X and 76 for our Y. So let's go ahead and insert this into our plot and see how it looks. So this is just, I'm gonna take this title out, I don't need it actually. And we're gonna add legend. So this is for our clean Y. So here, we're going to introduce into this graph, we're gonna select data. We're gonna add a new data set for X outlier. Our X is there. Our Y is there. What you're gonna notice is all the points overlap except for that one, right? The reason we call this an X outlier is if we were to draw lines bracketing our data in the Y direction, this point still falls in that range. It's not an unusual Y value. Looking at it, we're like, no, that Y value makes sense. It's in the right range. But if you draw a block around where we expect our X's to be, it's way outside. That's what we refer to as an X outlier. So we define them. They're much rarer. The reason they're much rarer is normally the X is the variable you're controlling, right? So normally that's not going to be an outlier. Normally you're going to have control over it. So what's going to happen is that means that either you, the most common cause of an X outlier is actually you wrote something down wrong. Because you're controlling that variable, so very likely it was supposed to be another value, but you were typing it in and you screwed something up. That's the most common cause of an X outlier, because it is an independent variable. It is something you're controlling. Remember, X is independent, Y is dependent. Now, what if we have a Y outlier? Y outlier, we're going to go the other direction. So let's grab our data. Let's create a Y outlier data set. And on the Y outlier, let's go back to that same value that was 20 and 76 before, or 6 and 55, and let's make it 6 and 110, for instance. So then we're going to insert a new data set. Chart design, select data. We're going to add a Y outlier data set. We're in this, let's see. Our X is here. Our Y is here. Now, what do you notice? If we go back to those brackets again, in our Y area, am I backwards? No, that makes sense. If we look at our Y bracket, it's again 30 to 80. It's up here to 110. It's an unexpected value, especially when you look at it within the X regime. and it falls perfectly in where we expect the x's to be. This is what's known as a y outlier. Why do we care? Well, because the way they influence your system is considerably different. And what do I mean? Well, let me show you. Let's put in trend lines. We expect this to be linear. I'll tell you that because I've designed it to be linear. So I'm going to go to, see if I can get to my, I want to find my, there we go. That's my clean data that I'm on right there. So I'm going to do add trend line for my clean data, linear, and let's look at our equation and our intercept. So for our clean data, and I'm just going to put them in order. So like, it'll go clean, x outlier, y outlier. That way you can see the equations. And you can see we have an r squared of 0.9746. We have a slope of 4.84. And we see an intercept of about 25. Everybody comfortable doing this? Cool. Did I give you the full spreadsheet, or did I give you just the clean one? Okay, I just want to make sure, because I couldn't remember if I gave you the full one or not. So, now let's do the trend line for our x outlier. So all of our data points are identical except one of them. Watch what it does to our trend line. And actually, I'm going to make these colors, the colors of the font match, so that we can easily identify which one's which. Or the same color family, I should say. Let me make that a little darker. There we go. All of a sudden, one data point being wrong, our slope's cut in half. Our intercept is increased by almost 50%, and our R squared's gone to garbage because of one data point. And it's one data point that's an X outlier. Now, let's introduce the Y outlier, trend line. So there we go. Add trend line. Color the font to dark green. What do you notice here? Our trend's not that different, is it? Slope's 4.8455, 4.8455, doesn't change. Our intercept shifted up by 5. That's significant, but it's only a 20% change in our slope, in our intercept. If you fit this, your R squared's terrible. Which of these trend lines to you looks closer to our clean data? The X outlier or the Y outlier trend? The Y looks much better, right? Comparing it to your data. But according to this, your X is a better fit. X outliers can skew your model far worse than Y outliers and still look better. And this is always true. It is the weirdest thing I've ever seen in data, but this will always happen. So X outliers are far more dangerous than Y outliers because they can give you a major shift in your model and you don't realize it because that point's influencing it. This is why outlier detection is critically important, because the X outlier versus Y outlier identification is a huge deal. Does this make sense? How we define X out? Okay, so I'll ask y'all, how do you know if it's an X outlier? Exactly. If you draw a box around the rest of your data, the X and Y, and it's outside the box of the X's, that's indication of probably an X outlier. Now, you can't do that with the endpoints, obviously, because the endpoints are always, if I draw the excluding the endpoint is a challenge, unless it's way off. That's the key. And then the Y outlier, the same rule. If it's too high or too low compared to where you think it is, but it's still in the right X bracket, you're fine. Is everyone comfortable with this? Like I said, this is something that's really interesting. You probably have never thought of it this way before, because honestly, until I really dug into data analytics, it never really clicked that this is such a big deal. But then once I saw it, I was like, oh, this is kind of a huge deal. Now, for the fun stuff. Points that technically may not be outliers, but may cause you far bigger headaches than you could ever imagine. Let me find it. Where's the piece I'm talking about? That's what I was looking for. Wasn't it? Oh, no, there's what I'm talking about. Next thing we're talking about is a leverage point. Anybody ever heard this term before? With respect to statistics? Anybody? Okay, cool. Good. I want to make sure I'm teaching y'all stuff that you've never seen before. This is a data point with the following properties. X value is unusual, ordinarily very high. Y value follows the trend. What do I mean by that? Imagine I've got my data points looking like this, they're showing like a line, and then I have a point there. It looks like an X outlier and a Y outlier, functionally. But if I draw the trend line through this, it sits on the trend line. Would you consider that an outlier? If you plotted it? No, right? Like, it's following the trend exactly as you expect. But it's called a leverage point because of how much influence it has over the system. So we're going to go through this again. Let me, I'm going to get this clean data, and I'm going to just move to a new graph so that we're not cluttering this thing. And we're going to introduce our leverage data here. So for our leverage, again, we're going to start with the same data set, but I'm going to change one of them. Or I'm going to add a leverage point, okay? And I'm going to add a leverage point that's, well, X is 120, or X is 20, Y is 120. Let's see what happens here. So let me grab this, insert XY scatter, get this, get rid of this name, we don't need it. So I did it the much easier way. Kill the chart title, let's add legend, let's add trend line, let's give that trend line the information it needs, so, oops. There we go. Equation, R squared value. Let's make the font on this blue so that we know that it's what it goes with, so there we go. Now let's introduce our leverage point. So, let's see if I want to add data to this. Chart design, select data, add, leverage. And hopefully it's very obvious what's happening here when we do this. I'm going to edit this one because I want to call this clean, so we know what it is. There we go. And let's add in, let's do a trim line for this one. Let's make it font on this orange so you can see it. Okay. This data point has the ability to alter my trend line significantly by just shifting that data point a little. So, look at it right now, we're sitting at 0.476, we're very close to the same equation, right? And we have an x and r squared value. Now, what if I take this to 140? My slope has increased by almost a full point. My intercept has decreased by 5 points. My r squared actually is better than the other data. Let's say I take this to 160. My slope is now 1.7 higher. My intercept is 10 higher. My r squared is still 0.96. It follows the trend. It fits that data as well as any other point there. But that point has so much leverage because of how far away it is from the other data points. Think of it as you have a pivot on an arm. Moving it a little bit here moves it a ton here. That's what it's doing, is it's dragging that tip up or down considerably by being so far outside the other data. This is what's known as a leverage point, and as a rule of thumb, you want to avoid leverage points if at all possible, because of how much influence they have. If you have all the data up to here, great. But if you've got this guy that's way outside, you are better off ignoring it than using it, because of how much influence it has over the other data points by themselves. It can cause as much damage, far more damage than a Y outlier can, because it's functionally an X outlier. And X outliers are the most dangerous outliers for that reason. But this one doesn't appear to be an outlier because it falls on your line. Does that make sense to everybody? This is a really important thing to know when you're dealing with models because of that behavior. So a way to think about this is like, there was a study where most of the individuals weighed around 200 pounds, and they had one person in the data set that weighed 400 pounds. And they were looking at muscle mass and power in these people. And the 400 pound had a very high Y value. It was also really strong, by weight. But everybody else was basically clustered around 200. So they were like this, almost like a cluster. There was no trend in the data. The data kind of looked like this. So let's, you had, say this is your 200 point, and then this is your 400 point here. And this was strength over here. So the 200s kind of look like this. There wasn't a lot of variation. And then you had this guy up here. And they went, oh, there's a trend. There wasn't, in reality. If you looked at that data by itself, there was no trend there. This forced a trend by being so extreme. And that's what it can do. It can actually define your data set with a single data point. And that's a massive problem when you're doing data analysis. So make sure, in order of importance, X outliers, identify them, get rid of them. Then leverage points, because they're arguably worse than Y outliers. Then Y outliers. It's kind of like your order of importance of getting rid of them. And in the category kind of is a leverage point, because a leverage point technically may fit your data very well, and it actually may be accurate. But the problem is you don't know, because you don't have enough data around it. And that's why we refer to it as a leverage point. The other one we're going to deal with is actually kind of more insidious, because it's hard to justify it. So I want to get rid of leverage points. This is an influential point. And an influential point is within the, I'm gonna put it in quotes, XY, the XY box. So it's within the logical range, but it's not falling on the trend. And therefore, holds undue influence. What do I mean by that? Well, let's go through the example. So I'm going to pull this down. I'm just going to reuse this and modify it. So this is going to be our influential point. And so this was going to be like x equals, let's say 6. Or no, sorry, we're going to be in this last one. We're going to say x equals, let's say 8.5, so within the range. Y equals 33. So it's in the box, right? It's in the proper range for Y and X, but it's going to cause headaches. Because I'm lazy, I want to do this. I'm just going to copy this chart, copy this chart down and manipulate it so that I don't have to. Here, that's what I want. There we go. Hold on, clean that set. There we go. So our clean data set looks the same. I'm going to change the names of these because I need to do that, or else it will bother me if I don't. So series 1 is clean. Series 2 is influential. It doesn't look inherently bad, but you can see it's not, and it's not moved my line a lot either, right? But it's destroyed my fit for the data. All because it's just not quite right. And if I move this point around, if I move it to like a position of 12 instead of 8.5, you can see how quickly that data point, by moving it around, I can change its behavior. Or let's put it at 11, let's put it right at the end. All of a sudden, it's still within the box. This is when identifying it as an outlier becomes critical. And this is those times where you may not have enough data to prove that this violates the z-square or modified z-square analysis. And also it's a y versus x, so you can't really use pure z-square or modified z-square, or z or modified z-score analysis, because it is not, it's a y versus x, it's not just part of a data set, it's not just part of an x group or y group. So what you have to do then is use this justification. You're going to show the trend with and without it, and how the R-squared is terrible with it, much better without it, and how it has undue influence on your model. You have to basically prove your point by excluding the point and seeing how it behaves. And so, do we have any other options? Well, we kind of do. We can do different ways of checking the behavior. So we can look at residuals. That's the first one. So what I'm going to do is I'm going to show you this example on the Y outlier data. and show you how we can kind of play with this stuff. So first thing we want to do is calculate our predicted y value. So and I'm just going to remind you that this is y outlier, so that we know we did this. So how do I get my predicted y value for my y outlier? Any idea? Because I have my actual data, right? Well, how do I get my predicted y? Well, let me ask you, what do we have over here that's useful? Yeah, this is our equation, right? That fits our data. So we can use this to calculate a y, and that's our predicted y. It says, hey, what does our model say y should be? So that's what we're gonna do. So I'm gonna copy this equation over here. I didn't want the whole thing. Okay, let me try that again. I'm just gonna put that down here so I can see it. And move it over. Let's just fine. Okay. So let's put this in here, and it's y equals 8455 times our x value plus 29.927. That'll calculate our new y, right? So we put it in, write it down, and this is what our prediction is. It says, hey, according to your trend line, this is what it should look like.
What was the equation again?
It's right here.
Yeah, I'm so behind.
Oh, it's this green one down here. It's our trend line equation from our graph. Questions?
No, it's okay.
No, it's okay. Ask.
I like lost everything, so I don't have any of it.
Oh, okay. So what I can do, let me, hold on a second. Yes, ma'am?
I'm also a little bit, I'm trying to keep up. I'm on the last, so on the third one on that page. I'm trying to see like what we needed for influential.
Okay. So what we'll do is let me walk back through all of them real quick for the data so you guys can be caught up. So let me see where you are. Oh, no, you're in good shape. You just need to put the equations on for your trend line. So click on your trend line and do display equation r squared. There you go. And that's going to be for your y outlier. Yep. And if you want to do your x outlier, you can select your trend line there and add your equations. There you go. And yeah, and then for the leverage, you're going to plot your leverage, which you have there, and then you put your trend line in for that also. Are you good?
Yes.
Okay.
I was trying to like catch up all.
Oh yeah, no problem. I want to make sure you guys get this because this is one of those things that's a little more insidious in your data than what we've been looking at. Like a lot of times your outliers are easy to identify. Sometimes they're this, and when they're this, what happens is you fit your data. You're like, oh, my equation looks good, but it causes headaches, and we want to discuss that. And then.
I just needed more data for the influential.
Oh, yeah.
Let me get finished.
Okay, cool. Let me pull that up. There you go.
So that one, it was just 11 and 33.
Yeah.
Be sure.
Yeah.
Thank you.
Yeah. And use these like to kind of play with it. You can see how shifting influential points and leverage points, you can see how it can drastically change your model. By just one data point moving even a little bit, it can throw off your whole model. And the closer that point is to your actual data, until it actually fits with your actual data, the worse it is because it's harder to identify. And that's why we want to talk about them in a little more detail. Okay, so we've done our y predicted here. So now we're going to do something that Excel does for us all the time. We're going to do this just so we can see it. We're going to calculate the residual for our data. What is the residual for your data? What does your residual represent? Y'all remember?
The distance or expected value.
Yeah, go on. What were you gonna say, Lucia?
No, I'm shy. I
No,
wasn't
you're
sure, I
fine.
wasn't
Okay.
sure. Please don't.
It's the difference between what your model predicts your Y to be and what your actual Y is. That's what your residual represents. It's basically like, hey, what's my leftover? What's my residual that my model didn't predict? My model says that at x equals 1, it should be 34, and my actual is 30, so there's something wrong here. Is really what it's saying. And so it's just y minus y predicted. That. So this is a great way of identifying immediately a point that's a problem. Without doing anything else, without actually doing z squared modified z squared, and even your z squared modified z squared, because you can't with this because it's x versus y, you can't do those, right? Because remember, z squared modified z squared are saying, for my collection of x's, is there an outlier? Or my collection of y's, is there an outlier? When you have y versus x, one variable influencing the other, you can't do that anymore. Because you can have a trend, you can have behaviors that are, that's looking at a distribution of one data set. This is actually two sets of data and how they interact. But what I notice here is this, residual -4, -5. These are all in the same order, right? And then I get to this guy. 51. That's kind of a dead giveaway that something's wrong with that point. When the residuals don't fit with the other residuals. When you're like, hey, my error on this data point is way worse, an order of magnitude worse than the rest of it. That is a quick identifier to go, something's wrong here. Sometimes it's not about a trend in the residuals, sometimes it's identifying that guy and getting rid of it. And this is an example where you wouldn't see a trend in your residuals, but you would see this laying there causing massive problems. This is another tool where you just go, my model might be perfectly fine, except this. So you take that data point out, you re-regress it, you check your residuals, and you go, okay, they now all look clean, what's my new model telling me? And I'm gonna ignore that guy because that is basically 10-fold greater than my average residual. Does that make sense? This is, like I said, this is a really important tool. I'm like, this is a huge benefit for y'all, and the rest of the class, I feel bad they're not here, because this is kind of a big deal when it comes to doing data fitting. If you want another way to see it, you can do what's called standardized residual, which will kind of help give you an idea of what it looks like. So let's do raw residual. I think normally we'll tell you the real answer, but standardized residual is another thing you can do. With standardized residual, what you're doing is you're saying, hey, there's a lot of error here, but is that really valid or not? Meaning, is that a big value, or does it just look like a big value because I'm looking at it compared to these? So what you do is you actually standardize it against your standard deviation, which your standard deviation says, hey, this is the error you should expect in your data based on what you've given me. So now we're going to normalize against that and say, well, how does it compare to what's the expected error? And this is kind of taking away the guesswork. So it's just your residual divided by your standard deviation, STD, I'm not going to do the calculator, of your population. So STDEV.P, that's the function. Standard deviation of the population versus the sample, because this is our whole data set, right? And then of your residuals. And I need to lock those cells because I'm going to copy them down. And I want them to stay the same, because the standard deviation is not going to change. It's the standard deviation for that set, so it doesn't matter which one we're looking at. So that's the equation. So for those of you who need to take a look at it and try it again. Now, do you understand why I used STDEV.P versus S? This is your whole population of data. This isn't a set of your data, so we're using the P. If it was a subset of the data, if we were using half of it, we'd say it's for the sample. But here we're using all of our data. And so if we look here, it actually makes it look even worse. It made this lower, but the ratio of this to these guys now looks a little different. And it makes it stand out more. These are all less than 1, and then this one's sitting up here at 3. It basically says, hey, the error for this is 3 times what we expect the standard deviation to be. What is our rule with removing an outlier according to standard deviation? 3 times. So this is a way to get that same z-score analysis, but in an x versus y data by using the residuals. And this says, hey, this residual is 3 times greater. So there's less than a 1% chance that this is real. And this data point is reliable. And we're using residual. We're actually analyzing the residual of the data to do this. And it works perfectly validly to do this. Does this make sense? 99 times out of 100, you can answer your questions with these 2 analyses and just know the answer and be done and not have to deal with it. Why does this work? Because your model isn't necessarily normally distributed, right? It's y versus x. You can't define a distribution on y versus x, or y versus x squared, or y versus some function of something, because it's not a distribution. It's a model. It's a relationship, a correlation. But residuals should be normal. It's a representation of the error in your model. If it should be normally distributed. If it's not normally distributed, then there's a trend in it, and then it's going to show up. If it's normally distributed, it's not shotgun blast. It's just a mess. So what you're doing is you're taking something that's non-linear, non-normally distributed, creating something from it that should be normally distributed, and then analyzing that normal distribution to see if it's true or not. And that's what makes this such a powerful tool, because it gives you a way to analyze data that you couldn't normally analyze for an outlier in any particular way. And this is such a powerful tool for that. Questions?
Can you show like how you get the standardized?
This one? Yeah. So that's your equation. So you're just dividing the residual by the standard deviation of the residuals. So it's this guy divided by the standard deviation of all these. And that doesn't change this value. The standard deviation piece in the denominator does not change. It's the same for every one of these. You can actually calculate it above and then use it if you wanted to, but I just figured I'd do it in the equation. Does this make sense to everybody? I recommend saving this spreadsheet, holding on to it, because this will help jog your memory when you're working on homework and you're prepping for the next test, because you're gonna be doing this like, hey, you're given a data set. Tell me if this is an outlier or not, and justify it as an outlier. And you're gonna have to do stuff like this. And your residual is gonna look like a shotgun blast, except you're gonna have this one data point that's way out there, but there's not gonna see a trend. You're not gonna see like a curve or a third order or a line. You're just gonna see this weird data point out there. This allows you to say, yeah, it is, because its residual is outside 3 standard deviations of where I expect it to be. And that's a problem. It doesn't look like regular noise anymore. It is now something wrong with my system. Okay, so now we're going to do something kind of weird, and I apologize for this, but it is kind of an odd thing you don't see. We're going to start taking data points out. This is what's called we're going to come up with the deleted residual. In the event that you can't justify it through these 2, you can go one step further. And you can do what's called the deleted residual. And it's exactly what it sounds like. We're gonna take our data set, and we're gonna, okay, what if I regress this, or what if I do my residuals, but without data point 1? And then I'm going, okay, what if I do it without data point 2? And we're gonna walk our way through every possible one that's gonna be removed. And we're gonna do the residuals on it. Because we're gonna remove it and then do the residual analysis functionally. And we have to do it for all of them, so that we can then go back and compare that one data point. It says, hey, if you're left out, how do you compare when the other ones are left out? So, I'll show you how the setup is. I would encourage you to take a look at it outside of class. I will post, actually I'm not gonna post this because I wanna give you all the advantage of you were here. So, I don't wanna take that away from you. I'll show you how to do it if we remove one and just know you would do the same thing, and then I'll explain the last part of it when we're done. So, if we have no x1 point, so this first data point, so I'm gonna copy my data down. I'm just gonna copy all, actually just my data, I don't need all that. So I copy this down. Let's put it here. Oh, let's try it again. There we go. And I'm gonna do this. Actually, I'm gonna leave it in because I'll show you what we can do in a minute. And I'm gonna calculate my slope, because I know it's linear, and my intercept for my data. Just so you know, you don't have to run a trend line to get slope and intercept. If you don't know, you can use the slope function. So it's slope equals, and then it says, hey, what are your y's? And you give it the y's. And it says, okay, what are your x's? And you give it your x's. It'll calculate your slope. Same thing with the intercept. If you say, I say equals intercept. And it says, hey, what are your y's? You tell it the y's. It asks what are your x's? You give it the x's. This is doing the same thing the trend line is doing. And then all I'm gonna do is I'm gonna take this out. Just delete that first data point. And you can see it updated my equation when I took the data point out. So I don't have to modify my equation, I'll do it on its own. And then I'm gonna do this for every single data set. I'm gonna do it for every piece of data in there. So I'm gonna, let's say, let me just pull all these over, and I'm gonna do, so here I'm gonna have no x2, here I'm gonna have no x3, no x4, no x5, equals slope my y versus my x. Correct what my label is, so I'm going to just copy this equation over here so that I can put my labels in. There we go. Slope, intercept, and this is equals intercept. My y's, which is this. My x, which is this. And then, let's delete that. Well, let me bring all these over so that I don't have to rebuild it every time. So that looks the same. Now I just go, okay, let's remove data point number 2. Delete, shift cells up, and it does it. Then I go to data set 3 and I go delete this one. Shift cells up. Let's go to 4. Delete. Shift cells up. And then 5. Delete. Shift cells up. So you just keep doing this through, we have up to 11. So we do this for where x equals 6, we have x equals 6, bless you, x equals 7, x equals 8, x equals 9, x equals 10, x equals 11. Does this make sense what I did here? I'm just regressing it with a data point missing. Then, we're gonna do, what is our deleted, what is our deleted y? Let's say deleted predicted y. So, for x equals 1, I look at my data where I deleted my x equals 1 data point. And I say, okay, my y equals the slope for that one times x plus my intercept. And it says, with this new equation, my predicted is 37. But instead of copying this down, I'm gonna do this calculation again, but I'm now, for data point 2, I'm gonna use the slope and intercept where I deleted data point 2. So, what is my predicted value for data point 2 when it's deleted, it's deleted from the regression? I say, okay, it's equal to the slope when there's no x2 point times my x plus my intercept. And I just keep doing that. For 3, I do it where I got rid of 3, so we'll do one more so you guys can see it. The slope of 3, when 3 is deleted, times my x plus my intercept. You continue this down, and then what this allows you to do is basically say, hey, how does my model change when I remove a data point? And then you're gonna calculate your residuals for each one of those. You're gonna say, okay, I'm gonna calculate now my deleted residual, or DRES, you'll see it referred to as both, is just equal to my y minus my deleted predicted y. And what you're gonna discover when you run all this is when you get down to this data point 6 right here, this value is gonna be enormous. Like here you see that it's like an order of magnitude, it's gonna be even bigger than that. And that becomes and then you can actually do a normalized residual of the deleted residuals, like the same way we did here, the standard residual. We can do a standard deleted residual, and it's gonna make that look even bigger. That's just another way that if this doesn't catch it, this definitely will. And what you're saying is, hey, how do my residuals look? And you go, hey, how would my residuals look if I got rid of that data point? How would it look? And so you then do it for each one of them. And the idea is you want to show that, hey, I delete data point 1, the change in my residual isn't huge. I really delete data point 2, my change in my residual model is 2. But then you get down to 11, you go, hey, I delete that one, my change in residual is enormous. And that shows you that data point's really, really, really bad. Does that make sense? If you guys want, I can actually post my example, because they're not gonna know how to interpret it. Let's be honest. You guys will, because you're in here, hopefully. Are you comfortable with this? Okay, I'll post my example after probably this afternoon when I get home. And then that way you guys can pull it up. You can see how it finishes out. I recommend completing yours. Make sure you understand how to do it, because this is going to play a role in the next exam. There's no way it doesn't. Because this is the first time we looked at identifying outliers in a group of X's or a group of Y's. We've never looked at how to identify an outlier when it's an XY set. This is how you do it. This allows you to say, hey, something's wrong here, I need to deal with it. Okay? And it's 10:10, so we are done, and you guys are one step closer to spring break.
Dr. Henry?
Yes, sir.
We didn't catch the water residual.
Yeah, it's just my y minus my predicted y with the deleted, with the function, with the deleted function.
Okay,
That's all it is.
thank you.
Oh, you're welcome. And then I'm actually going to show you like the next step, which is the standardized deleted residual. We're basically